Welcome to this interview with Klaus Lackner. I'm your host, Dan Miller. Dr. Lackner is sometimes known as the Godfather of carbon capture. He is one of the first scientists to explore how to remove excess CO2 from the atmosphere. He began this work at Columbia University and is now at Arizona State University. This interview is part of a series of interviews with climate scientists, technologists, authors, advocates, communicators, and others involved in understanding and fighting climate change. It is sponsored by the Climate Chat Club on the social platform Clubhouse. If you are a member of Clubhouse, please join our club. You can find other Climate Chat Club interviews by searching for Climate Chat Club on YouTube. And now, our interview with Klaus Lackner. Well, welcome everybody. This is Dan Miller, and you're in the Climate Chat Club. And today we have a very special room. We'll be interviewing Klaus Lackner about carbon capture. And we just spoke a little while ago about what the subject we're going to cover, and I know it's going to be a fascinating discussion. Anyway, today I would like to welcome Klaus Lackner to the stage. I've known Klaus for a long time, over a decade. In fact, I recall we met at his office at Columbia University at the time, and he gave me a tour of his lab where he was working on direct air capture systems back then, and basically taught me a lot about carbon capture way back when, and helped guide me as I invested in the space. And he's probably, I believe, one of the people that's worked on carbon capture really for the longest time, and wrote a seminal paper in Scientific American, if I recall correctly, Klaus, where you laid out what it was all about and really introduced the public to the concept. But rather than me talking, I would like to turn it over to Klaus and ask him to give us a bit of his background, like what he studied originally, where he worked, and what brought you, Klaus, to the field of carbon capture.
Well, that was a very long time ago. Let's go back to the early 90s. And I began to realize that the problem is not so much that we run out of energy, but that as we consume all that energy, we have a waste stream of carbon dioxide. We simply dump it to the atmosphere. And it had become clear by then that once that carbon dioxide is in the environment, it stays there. Now, a little bit of it ends up in the ocean. A little bit of it ends up in the biomass, but roughly half of the CO2 we put out is for hundreds of years in the atmosphere. And the combined ocean, biosphere, atmosphere, that excess carbon is with us for tens of thousands of years before it gets out. So it was very clear that if we don't run out of carbon, which we clearly don't, we have the capacity of creating really a mess. And sometime in this century, we have to go carbon neutral. And if we wait too long, as we probably have by now, we also have to go carbon negative. In other words, we will have to pull quite a bit of that carbon we have put out and will put out before we can stop ourselves. We will have to pull back out. So I see us over the next decades pulling 100 parts per million back, and figure out how to have an energy transition which moves from the current 40 gigatons a year put out into the atmosphere to zero, and ultimately a negative 40 gigatons a year, because then it takes us roughly 40 years to get that 100 ppm back out. So this is where we are. I started figuring out early on how to store all that carbon. The guilty party when it comes to say we should just make minerals out of it. We have the mineral resources to do that. And that's nature's way in the long term. If you have alkaline rock like serpentine and olivine and many other silicates, they gradually carbonate, and that's how we get rid of excess carbon. And we propose to accelerate this, and you see this going on at Klappfix in Iceland today. Then in the late 90s, I got interested in pulling carbon dioxide back out of the atmosphere, because roughly half of all the emissions we have don't come from point sources, but are distributed And some of those are very, very hard to stop. We probably will use hydrocarbon fuels to run airplanes. This may not be petroleum, it may be synthetic fuels we make from CO2 and water and renewable energy. Because once you have hydrogen and CO2, you can make liquids and you can carry them around, store them for years if necessary, and use them when you need them. But again, I would expect that in the long term to be on the order of 40 gigatons a year. Because if you look at current energy consumption, I was part of a paper a few years ago which said, oh, the last 20% are very hard to fix. But since we grow 2% a year, by the end of the century, we grew by a factor of 5. So that last 20% is again 40 gigatons a year. So, but then we recycle carbon in a closed cycle and we dispose of carbon to get back to a tolerable level in the atmosphere. And that's the racket I got myself into.
Very good. Okay. And you've been working on a particular kind of air capture system for a long time. I call it moisture swing. I do want to talk more about general carbon capture issues, but perhaps you could tell the audience about how your system works and what the key ideas behind it are.
Well, there's a certain amount of energy you have to pay if you collect CO2 out of the atmosphere. Thermodynamics tells you you can't do with less than 22 kilojoules per mole of CO2 to pull it out of the air. And by the time you compressed it to liquid fuel, you probably had to pay 40 or so. So that's the minimum you have to pay. On the other hand, if you burn gasoline, you got 700 kilojoules if you made a mole. So if we can get close to thermodynamics, this is all working nicely. But the moisture swing has one additional advantage. We can get that energy by natural means. The air is never saturated or rarely ever saturated in water vapor. And if you add water vapor to the air, that's going downhill thermodynamically. And if you can couple that to pulling CO2 out, which is what the moisture swing sorbents do, they love CO2 when they are dry and they hate it when they are wet. So you can absorb in the dry state, you put moisture on it and they release it. So you have a catch phase where you are outside. When it's dry, you collect CO2, you put it in a box, make it wet, and it releases again. So the moisture swings are particularly good at avoiding explicit energy. They pay with water, and it turns out water is also precious. But a cubic meter of water costs tens of cents, 10 cents, a little more, depending on where you are. Power plants get it for 5 to 10 cents a kilo. And if you take 50 cents for the price of water, you are still far cheaper than any energy source you could have. So this is cheap energy to put into the system. And water, in this case, acts like fuel. I sometimes joke we invented a glorified swamp cooler which collects CO2 rather than makes things cold. On the other hand, if you want to work in Singapore or in Iceland, the weather is usually quite wet or the air is quite moist. And in those cases, you need thermal swings. And we are working on this too, because one of our goals right now is to be agnostic to location. Because one of the advantages of direct air capture is you can do it where you want the carbon. And if you tell me I can only do it in the desert, then I have limit, and only in deserts where I have access to water, could be ocean water, then I limited my reach. And so we are working on being open to all of those. But the moisture swing is a good way of reducing energy consumption.
But even the thermal swing systems also use what I call earth energy to distinguish from man-made electricity or heat from fossil fuels. You're just using the natural energy of the earth. They use that in the cooling cycle, right? They use just free air.
Right.
So all these carbon capture systems, one of the questions people have about carbon capture is that wouldn't it use too much energy is one of the memes, I guess, out there. And so this is one way to address that, right?
Some of them do. If you make calcium carbonate and then you have to free the CO2 again, you just bought a lot of inefficiency because it takes nearly 200 kilojoules to drive the CO2 of calcium carbonate. So you are bound to be 10 times inefficient. On the other hand, you can, if you do it judiciously and you use cheap energy, you can get very low. On top of it, you could use renewable energy, but even then, you like the idea that the energy consumption is small because let's not kid ourselves, you pay for that energy. And so typically people talk 50 to 100 kilojoules is probably something where you want to end up. But that's still a lot less than you get out of a power plant for the same amount of CO2. Okay. As I just said before, gasoline has 700 kilojoules of energy in it.
Okay. Well, by the way, you're kind of hitting on something here a little bit. There's really two parts to carbon capture. One is to capture the CO2 out of the air, and the other is to do something with it. And some you could reuse it and use it for useful purposes, or you could also just put it back underground and keep it there, sequester it permanently. Can you talk a little bit about what you think some of the uses are of captured CO2 and your thoughts on is there enough room underground, for example, to put all this CO2 that you said we need to capture, the 100 ppm worth of CO2?
Yeah, let me start there because that's a fairly easy answer. If you look at what people who do geological storage tell you, there's plenty. Now, by the time you subtracted the places which didn't work so well or where public resistance is high, it's not quite clear that it's still that big. But if you look at minerals, which you can carbonate, you run out of fossil carbon before you run out of storage spaces. Many years ago, somebody asked me, but those serpentines are rare minerals. And I said, yes, but they are far more common than coal. And he said, I have to agree to that. So I think we have the capacity to clean up after ourselves. I think one can make the case that we shouldn't willy-nilly use this storage capacity for unnecessary future emissions. We should work hard to get off those emissions. But at the same time, if you ask, can we squirrel away 100 ppm of CO2, which adds up to roughly 1,500 gigatons of CO2 that have to be put away? Yes, I think we have this. If you look at one place where this needs to be demonstrated soon, there is Kopfix in Iceland, and they are putting more and more CO2 into those basalts. And it looks like you can do this as a fairly large scale, but Iceland is small. But if you look at the geology they are taking advantage of, you find that all along the mid-Atlantic rift. You find this in many other places of the world. Basalt floods. Basalt is very common all over the world, so we can find easily enough storage capacity. And direct air capture has the advantage that you can collect the CO2 where you wanted it rather than have to ship it over thousands of miles from some source to the place where you want it. If you take CO2 out in a basalt area, the effect of having removed it is visible all over the world.
And by the way, I think just for the audience benefit, I want to clarify a few things that you were talking about. So Carbfix is a company that's operating in Iceland that takes captured CO2 and puts it underground. They basically, I would describe it as injecting club soda. They mix CO2 with water and inject it in the ground. And there's a special formation of basalt you were talking about that when they react with carbonated water, it carbonates. How would you describe it? It turns to rock, is the way I describe it.
Yeah. In 2000, in the time frame around 2006 or so, I and Wally Barker went to Iceland a lot, convincing the Icelandic government that this is a good idea. So Reykjavik Power went behind this Carbfix project. Mm-hmm. And first they just put tiny amounts into the basalt. And the exciting part was everybody said, well, you inject it there and the CO2 will hang around forever. But it turns out they could demonstrate that it literally in a year or two solidified into calcium carbonate in these formations 800-900 meters below the surface.
Wow.
And so they send club soda down, and down there they form hard rock out of the CO2 they injected. And the net result of that is that it's now permanently stored on timescales which are geological. And you need very special formations. You need to be wide open so you can pump the water in without a big energy penalty. They can do this right in Iceland, but I'm arguing they also need lots of water, and they could use ocean water. And these formations continue as what is known as the Mid-Atlantic Rift all the way to the Southern Atlantic. There are plenty of other such formations all over the world. Which could handle this, and particularly if you're near an ocean, you have unlimited water supply, so you can actually run this. And so I see this as one of the big storage capacities. And unless they run into a severe snag, which you never know until it actually has been scaled up, there is every expectation that this alone is so big that it could take all of the CO2. But we have backups, right? You can make biochar, you can put geological storage in. There are plenty of other
What do you think of injecting into saline aquifers? There's a lot of room there for CO2.
There's a lot of room there, and the big question is what fraction of all that room is actually good? And if you take the Department of Energy's numbers, it is so large that we can't possibly run afoul of limits there. On the other hand, not every project worked. For example, in Insala, they stopped after a while because they didn't really understand the formation, and the flow of CO2 underground was different than planned. So so just like in oil exploration or gas exploration, you drill dry holes. Here you will drill leaky holes. Mm-hmm. And so you have to figure that out, do the characterization. And at the end of the day, my expectation is it's not quite as much as we think, but it's a lot more than we need.
Okay. So just to recap, because I think one of the questions people have is, what are you going to do with all this CO2? And they just can't imagine there being room. But then I point out that all that CO2 came from underground in the first place, in the form of hydrocarbons. But
and the hydrocarbons are a small part of the total,
right?
Because as you pointed out, the saline aquifers don't have hydrocarbons, and one of the classic examples is the Utsira formation in the North Sea, which people have argued is by itself large enough to take all of Europe's CO2 for 100 years or so.
Is that the one where they first started testing injection?
That's where the first injections in Norway started.
And how long ago was that?
People
don't realize this has been going on for a long time already.
They started in 96 or so, right. And this was driven by the fact that the state of Norway put a $50 or $55 tax on CO2 emissions of certain flavors like this one. And they had natural gas with 10% CO2 in it. They needed to remove the CO2, otherwise they couldn't sell it. And so now they decided, in order to avoid the tax, they inject 1 million tons a year into this formation, which seems to have nearly unlimited capacity. So this is a good example. Insala in Algeria was a bad example, right? So just like with drilling for oil, I think we will find out that this capacity is large, but not every formation works. Mm-hmm. And so we'll sort that out. But my point is we can put 1,500 gigatons of CO2 away, and we can even put a little more away if we have to.
Okay.
And on the other hand, what can you do with the CO2? Current markets for CO2 are woefully small, right? If you look at the US, we probably consume 100 million tons of CO2, most of it in enhanced oil recovery and urea production. Mm-hmm. The rest of what I would call merchant CO2 is maybe 10 million tons.
Right.
But we put 5,000 or 5,300 million tons of CO2 in the air every year in the US. So the amount we consume is a rounding error on what we are putting out.
Right, and people often wonder, and I think you're getting to the point of people wonder, well, why why hasn't CO2 from the air, capture of CO2 from the air, why hasn't it scaled already? And I usually point out, well, there's no one will pay you to do it.
Because nobody asked for
No
it.
one asked for it. No one will pay
Nobody
you
asked
until
for
very
it.
recently. It's changing right now. Can you comment
Right.
on how it's changing in terms of like
Well,
small scale incentives now?
in
Climeworks in
the
Iceland, for
in the
example.
last few years, the federal government put up a tax rule which basically says that 45Q, which basically says that if you collect CO2 from the air and permanently sequester it, you get a $50 tax credit. If you make a low carbon fuel, or for that matter, sequester CO2 from air capture, California pays you the CO2 fee for the low carbon fuel standard, which currently trades somewhere around $190, $200 a ton. You now have private companies like Stripe and Microsoft say, we need to get our CO2 under control. And they are paying substantial amounts of money. There's an air capture company in Europe where Stripe is paying on the order of $700 a ton.
Right, that's Climeworks, is that right?
That's Clamber.
Right. By the way, for disclosure for everybody here, I'm an investor in a company called Svante, and Svante that's a carbon capture company focused more on point source capture, but they are partnered with Climeworks to share their sorbent materials that will help lower the cost that Klaus was just talking about, $600 a ton, to bring it way lower. And so this is an area that I've been interested in for a long time, for the same reasons, by the way, that Klaus got into it earlier than me. But then I also realized that this was not going well, that we were continuing to emit CO2 and not doing what we needed to do, which we were warned about in 1988 by Jim Hansen's congressional testimony. And since that time, we've doubled our emissions rather than cutting them in half. And so I realized also, like Klaus did, that we're going to be in trouble. And that's why all this interest now in carbon capture. So just to summarize on the getting rid of it part, there's some things. Oh, you mentioned turning it into fuels. Can you maybe expand on that? That's an area people might not realize about.
The the big market for carbon, which is the problem of all that CO2, is of course fuels. So what we do right now, we take fossil carbon from underground and we dig it up, we extract it by whatever means, and then the next thing we do is we oxidize that carbon so that we get our hands on the energy, and then we dump the CO2 because we don't need it anymore. And that's that 5,000 million tons we put out every year. If we could make fuels from renewable energy and CO2 and water, basically use the renewable energy to unburn the CO2 and water back to the hydrocarbon it came from, then we don't need petroleum, then we don't need gas or coal. We can simply have liquid fuels where we need them, where we want them. They are now probably a bit at a premium relative to other forms of energy. So if you can use electricity, but if you can't, like in an airplane, make your fuel by harvesting CO2 from the air, by taking water, which is small amounts compared to our daily water consumption, and then use the energy from renewable energy and split the water into hydrogen and oxygen, and use that hydrogen first to remove the oxygen from the carbon and then bind to the carbon to make hydrocarbons like gasoline, like jet fuel, like diesel, whatever you want to make, natural gas, methane, it's not natural anymore, you can make that way. And so you could feed back into the economy whatever hydrocarbons you need. Now, the markets will figure out where the balance between hydrocarbons and electricity and batteries and all of this will be. But planes and ships and heavy trucks probably do better with liquid fuels. And if you are in winter in Boston and it's dark and not windy but very cold, probably your best bet is to burn fuel to make electricity so you keep the heat on at home. That fuel may very well have come from the southwest and have been produced sometime in the summer when the solar panels and the windmills produced more energy than you needed.
Okay.
And by the way, the CO2 you can now freely emit because those plants right next to it will collect CO2 out of the air again and close the cycle. Now, you could also collect the CO2 and ship it back 3,000 miles, but I'm willing to bet that the pipeline is too expensive to make it worthwhile.
Okay. So, as you pointed out to me earlier, this is a carbon neutral process, not a carbon negative process, because you take CO2 out of the air, which is carbon negative. You then make fuel out of it, and you put it in an airplane. The airplane flies and burns that fuel, and therefore releases the CO2 back to the atmosphere. So the same amount that you took out goes back in, roughly speaking, and therefore it doesn't lower CO2 in the atmosphere, but it does prevent you from using fossil fuels, which would increase atmospheric CO2.
Right.
Do I have that right?
And so I see direct air capture service two markets. One is it will close the carbon cycle, and currently that's 40 gigatons a year of CO2 sloshing around in this cycle. And if we only deal with 20% of it, but let it grow to the end of the century, it's again 40 gigatons a year. And because energy consumption worldwide, keep in mind, developing countries still have to develop. It grows 2% a year. So we may very well end up at that number. And then on the other side, you need to put CO2 away. And roughly speaking, 1 ppm of CO2 in the air is 7.5 gigatons of CO2. On the other hand, if you remove CO2 from the air, the CO2 that escaped into the biomass in the ocean will also be released again. So roughly speaking, you need to do 15 gigatons a year, which basically says if you want to climb back out of that tree and come down 100 ppm, you need to store 1,500 gigatons. And in round numbers, that's 40 years at 40 gigatons.
I'd like you to address, there's a lot of talk among even climate advocates, advocates for climate action, and some of them disparage carbon capture as being a problem for a variety of reasons. Very, very often they say it's unproven technology, it can't scale, it uses too much energy, et cetera, et cetera. There's no, maybe they wonder if there's room underground for all of the CO2, which you just addressed. But to the folks who wonder, first of all, is it a real technology? People think it's fairy dust or something like that. Can you please address the issue of whether capturing carbon out of the air is feasible in a practical sense?
Well, when I started in 1999, and I was the first to say, look, we need to balance the carbon books, and air capture is probably necessary, and we'll hope it's doable. The first response was it's physically impossible, it's thermodynamically impossible. The claim that it's thermodynamically impossible got shot down. Among other things, I wrote a paper where I was horribly pedantic about the details of thermodynamics and worked out it's just fine. Then people said, well, but in practice we don't really get there. There's Sherwood's rule, and meanwhile that got put aside too, and in part because by now there is no question that it's practically feasible. On the other hand, it is not free, and my guess is the current practical applications out there are around $500 a ton, and that's 10 times more expensive than we would like it to be. And at $50 a ton, the capture of CO2 from air is not a critical budget item anymore. You can see it actually quite simply. If you look at a barrel of oil and you compare to that, well, a barrel of oil makes 0.4 tons of CO2. So at $50, that CO2 would be $20 per barrel of oil. Now, the price of oil has gone up by far more than $20 a barrel up and down, and the world has not come to an end. Put another way, it's about 42 cents per gallon of gasoline. So if you made synthetic gasoline from CO2 and water, the cost of your CO2, which entered into that gasoline, would be 42 cents. So we clearly could afford things at that level, but at $500 a ton, it's a little steep. On the other hand, we had a similar situation, but a very different discussion in the 70s about 60s and 70s about solar and wind, because solar and wind at the time were 100 times too expensive, and they have meanwhile come down. Solar photovoltaic energy has come down by more than a factor 100. Now, in mass manufacturing, there's a rough rule of thumb which says the costs come down by roughly 20% for every doubling, cumulative doubling. And if you apply that rule, you find out that means that if you grow 1,000-fold, your cost comes down 10-fold. So photovoltaic had to grow from kilowatts, not just to megawatts, but to gigawatts in order to grow enough, and it did that. It got help, it got subsidies, it got sponsored, but it made that growth, and now it's there. Air capture, on the other hand, only has to grow a factor 10, get cheaper 10 times, which means it has to grow 1,000-fold in size. Now, right now, it's maybe kilotons a year. So we have to go from kilotons to megatons a year. Megatons a year are not affecting climate change, one way or the other. They are just too little. They are putting you on the scale at which the US consumes CO2 in filling fire extinguishers, making fizzy drinks and beer. And if you add all of those various and sundry things together, you are at 7 million tons a year. So by the time you reach that scale, you would have come down by that factor 10 you're looking for. How deep you can go from there, nobody knows. But given that you can get there, you can now ask the question, if we were to subsidize this, think of having reverse auctions like people had for photovoltaics, and somebody, a government or philanthropy, swallows the difference between the $100 you can get in that market and the initial price of CO2, which is higher. You can then ask, how much does it cost you to drive the cost down to $100? Well, we did a study and a sensitivity study, and I can tell you that we came up to the conclusion that with 60% probability, you spend less than $200 million. With $1 billion, you have a 70-80% chance that you actually succeeded. Now, that is a small amount of money. So, yes, the technology is unproven because nobody ever asked for it, and it's brand new. Right? Cars were there in 1900, jet planes were there in 1950, and eventually you only get proven by actually doing it. Now, if you spend $500 million on this, you actually know the answer. Either this is a technology like the vast majority of successful technologies, and it comes down in price as it scales up, in which case you're in good shape because now you know that you can do it, or it turns out it cannot. And for $500 million, that's not a bad thing to know, because now you desperately need a plan B, and that plan B, as far as we can tell right now, doesn't look very good, because we cannot grow enough trees to collect all of that CO2, and we don't really have all that many good options to operate at that scale and not create havoc on the environment. Direct air capture technically scales much better than anything else.
Actually, can you talk about that a little bit? That's a good point, because I think some people worry that air capture will be an environmental disaster, when actually I think it's, as you just pointed out, it's the one thing we can do. It's sort of reversing what we've done, and it's the least impactful of all the, I guess, quote, geoengineering techniques of, lowering the atmospheric CO2 artificially. Can you talk a little bit about the safety of capturing CO2 and sequestering it?
Well, let's begin though with the environmental footprint, right? 1,500 gigatons of CO2, which is that 100 ppm, is roughly speaking 400 gigatons of carbon. All the forests in the world contain 600 gigatons of carbon. How do you feel about forest fires? How do you feel about the environmental footprint of collecting CO2 by biological means at a scale which is larger than agriculture? I think you will see an enormous environmental footprint, and you will drive up the cost of food right when people need it. So there are the challenges on this side. Here, because a mechanical tree is, this is what our colleagues who work with us, Carbon Collect, call their devices. They collect about 1,000 times as much CO2 as a tree of a similar size would. So therefore, your footprint is a lot smaller. You are not emitting anything to the environment. You're collecting things from the environment. So your footprint is a lot smaller than with many other options. You don't put fertilizer out. So these things are quite compact and small. Many years ago, before I even lived in Arizona, I worked out that you could collect all the CO2 for all the world on a footprint the size of Arizona. And you wouldn't even have to fill it up, because what really limits you is that at the back end of Arizona, you are out of CO2 in the air. You can't compress these things more tightly without them interfering. But you would cover maybe 1% of the land. Now you can spread this over the planet, and then the footprint becomes even smaller, and you can do it in places which are well suited to that, which have the resources you are looking for. You will need energy. That could be wind energy or solar energy. You will need some water if you make fuel. You will need some water if you run a moisture swing. So you probably are near water, think oceans, and you can work all of this out. And your footprint is quite small. You would need, if we argue you can put a ton a day apparatus into a shipping container. 36 gigatons, that's the 365 days in the year. 36 gigatons, therefore, would need 100 million shipping containers. Shanghai Harbor has 30 million shipping containers a year leaving there. So there's a production capacity on that scale.
Wow.
In near Shanghai, which can do more than you would need to do here, because think of the 100 million shipping containers. If the machines last 10 years, you need to make 10 million a year. We make 90 million cars and trucks a year. So the car industry is larger than that. If you look by revenue, this air capture industry would be comparable if it did everything and not just be part of a larger picture. It would be as large as the aviation industry and somewhat smaller than the energy industry. So from a conceptual scale, we know we can get there. The question is whether the technology will oblige and get affordable. And I see no obvious reason why not. There are plenty of other technologies which have done it, but I'm also the first to admit you only know after you did it. Right? The proof is in the pudding, and I can theorize over that as long as I like, and I can tell you that if this technology follows, in general outline, advances made in other technologies, then we should just be fine. Could it be that this has some obscure obstacle we don't know about? Yes, it could. But then I'll challenge you to the plan B. People have asked me, can you promise that it works? And I said, no, I can't. But I can promise you if it doesn't work, it'll hurt.
Right. Speaking of that, you and I, about 10 years ago, kind of did a rough back of the envelope calculation of what it would cost to do just what you were describing. Build, I think it was there we were shooting for 40 gigatons, basically to offset all of man's fossil fuel emissions, basically. Mm-hmm. And I think we came up with 110 million, therefore, devices, shipping container size 1 ton per day or 365 tons per year systems built over 10 years, as you described. So that was like 11 million. And we came up with a cost, I think we were estimating at gigaton scale. You said it's currently somewhere in the $600 a ton range today, but would get down to about $50 a ton when we scaled up to that size. Do you
Yeah.
recall that and how much the total would cost and all of that per year?
Well, there are two ways of looking at it. My simple-minded approach is if you tell me that a ton costs $50 to pick a number, right? Then that includes all the capital costs you have to put up, right? Because otherwise, you need to sell your CO2 waste management at a higher price. But if that's $50 a ton and you collect 40 gigatons, that's $2 trillion, right? That's your revenue stream.
Mm-hmm.
Yeah, I think the aviation industry, including everything, airlines, Boeing, and whoever else makes airplanes, and all the subsidiaries and suppliers, adds up to a $4 trillion industry.
Wow.
The world has a nearly $100 trillion GDP.
And I tell people that it would cost, as you said, $2 trillion a year. And I said, that's a bargain compared to the cost of not doing it. Like, what would be the damage from that amount of CO2 in the atmosphere?
I also would point out numbers always look horrible if you put them that way. Right? Mm-hmm. I once pointed out to people, just to make this point, if you had all the cars in the world come out of one factory and they have to drive along a line to park in a straight line outside the factory, it turns out the last car made at the end of the year cannot drive to the beginning of the line because it's too long. It'll break down before it gets there, right? So you can, there are a billion cars on the road, right? And here you need 100 million of these devices.
Right.
So on the scale of things, this is undoubtedly a large industry. But then it's a derivative of the energy industry, which is even today larger than that.
Okay. Hey, before we open it up to audience questions, I'm going to ask you one more question, because there's again a lot of people who wonder whether this is possible, and of course it is possible, as you pointed out. It's actually already operating today, so whether it can even exist is kind of proven already. And then there's the question of scaling. I think you've addressed that well. I mean, there could be bumps along the road, but if it's like most other kinds of systems that we've developed, we'll learn as we scale up. And there's a lot of room to put the CO2. So we covered all that. Then people also come up with this, and they say it's a moral hazard. If you think you have the capability to take CO2 out of the air, then you will continue polluting the earth, et cetera, with fossil fuels on and on. Can you address that question of the moral hazard?
Yeah, let me try this 3 ways. First of all, this is a very good discussion to have in 1980.
Right.
By now, we are past the point of no return. We took our moral hazard without having the the assurance that we can do something with it, and it's now too late. There was a paper on the trouble with negative emissions a few years ago in Science, and one of the arguments in there was that we can't do it because it's a moral hazard. And I got 40 plus people to write a response, and in there we made a point. We said, if somebody already has fallen into a raging river, throwing a life preserver after him doesn't guarantee that I can pull him out, but it's not a moral hazard. And the argument that he won't learn how to swim because we throw this thing is probably not a good idea. And the response was, well, yeah, but you shouldn't egg him on to jump in because you say you have a life preserver. And I think this actually comes down to where in the spectrum we are. And I would argue that some of the people who bring this forward actually have not yet accepted how serious the problem really is, because they play, in effect, chicken with the problem. Right? They say, we don't really want you to solve it right now, because then you do it a way we don't like you to solve it.
Was Kevin Anderson?
Right? Yeah, because
did Kevin Anderson write that paper, The Trouble with?
There was
somebody else.
I believe.
Yeah,
so,
because
yes.
He was. We interviewed him.
Anderson and Peters,
right. But we interviewed him a few months ago, and I asked him specifically about that. And he actually, I guess, I don't know if he's changed his tune or he was just clarifying. I think he was clarifying, but he said, carbon capture, the carbon capture technology is not a moral hazard. He said using carbon capture technology is not a moral hazard. He said the moral hazard is using the excuse of carbon capture technology to avoid doing emissions reductions. And and so I would agree with that. I mean, we in order for 40 gigatons to have a negative effect on the atmosphere, we have to stop putting up 40 gigatons. And if you're going to continue on, it's a very expensive way to continue on the way we're going.
Yeah, I think my point earlier was it's now too late to say we don't do anything.
Right.
And it's nice to have something in the pocket in case we need it. I would be very clear that we now live in an overshoot world. We have overshot. And right now the issue is how far will we exceed the safe limit and how long will we be above it? Yeah. So at this point, we need to do everything we can to get back down. And part of that is getting negative emissions going as fast as you can. And by the way, we need to use the biomass versions of this too, because they are ready to roll. They may never reach scale, but every little bit helps because we are not just putting on the brakes right now. We have to return back as fast as possible to where we were. And any ton not emitted is helpful in this case.
By the way, maybe I'll finish with that question, by the way, because you reminded me of a question I should have asked. In that we've been talking today about man-made mechanical systems that take CO2 out of the air. And there's a bunch of people working on what's called natural systems, where you enhance some natural way of doing things to absorb carbon. You might grow kelp in the ocean and hope it sinks to the deep part of the ocean. You might drop iron in the ocean to hopefully grow algae, which would then again sink to the deep parts of the ocean. There's a bunch of those schemes. What are your thoughts on the natural ways of sequestering CO2?
Well, let me start there. 40 gigatons of CO2 a year represents a certain amount of energy we got out by burning that much carbon. If you ask how big has to be the sunshine area to do enough photosynthesis, and all of the examples you gave are related to that, it's bigger than the world's agricultural land. So, wow. First of all, you put a real strain on the capability of feeding people. And secondly, if you do something akin to intensive agriculture, because a forest by itself is not collecting much CO2 unless you push it, you get a very artificial environment. And some of the things with kelp, I'm not even convinced they work, at least not on a large scale. Because do you really want to make a manure pile at the bottom of the ocean at that scale?
Okay. Yeah, and the other one you were talking about was if you plant trees. That's the one everyone thinks about. We'll plant 1 trillion trees. I also point out to them that you're storing that carbon.
Go ahead. We need 1 billion mechanical trees or 1 trillion natural trees. Okay. On the other hand, how big is a tree? How many tons of carbon does it contain? There are only 600 gigatons of carbon, so in biomass as a whole. So those trees are not very heavy. There are a few trillion trees on the planet. and you are largely changing environments and landscape because you do agriculture. If I look at biomass examples, people are very proud of making ethanol from corn, from sugarcane in Brazil. And then people later pointed out that was a really non-desirable impact on the Amazon. Then we came along and said we make bioethanol. Currently, 40% of our corn crop substitutes for a couple percent of our energy.
Yeah.
You cannot get to 100% that way. There's a reason the Brits ran out of wood in the 17th century. Mm-hmm. Yeah, because they couldn't supply the energy demand. And the third example is the Europeans under Kyoto started palm oil plantations in Southeast Asia, which was from an environmental perspective a disaster. if you get to these scales, you are not benign anymore.
Mm-hmm. Okay, and I also point out that if you bet on trees, and climate change will continue anyway, and we get to 2 degrees warming, and we have 10 times the forest fires we have today, those trees are burning down, or they're getting flooded out, or they're dying from heat stress or bark beetle or something like that, and you bet on that to keep you
But,
safe, and it's at the worst possible time you find out that you're not safe.
well, put another way, deforestation contributed to climate change, but it's a small contributor compared to CO2 from fossil fuels.
Mm-hmm.
So clearly, you cannot collect all that fossil carbon by putting the trees back, which were there in 1800.
Mm-hmm.
So you are building vast forests where there weren't any. And the CO2 we put out, the carbon we put out, is with us for tens of thousands of years. So you are now responsible that these forests do not go away, not just for 100 years, but for 10,000 years. And how do you give that assurance?
Right. And someone else said you should do reforestation to address deforestation, and you should do geologic sequestration
Yes.
to address geologic emissions. And I think that's a kind of a good way to put it.
I think that's a good way of putting it. I also would argue we can certainly go over this for a while because that CO2 is held in place probably for 50 years. Mm-hmm. And it may buy us the time to actually get technical solutions which are permanent in place by then. We got to cut down that overshoot. And the idea that the overshoot is free and all we come to is come back at the end of it and everything is as good as it was before is simply wrong. If you melt a glacier, it doesn't come back simply because you changed your mind about the sea level.
Okay. So I'm going to invite people to ask questions. Please keep it focused on relatively short questions for Klaus. Start with David. David, welcome to the stage.
Thank you. I appreciate it. You answered one of my questions about fuel development, fuel production from sequestration. But the other one was I've read about using sequestration with prefabricated concrete and building material construction. If you could talk about how that, what the possibilities are on sequestering CO2 within concrete or cement production. Thank you.
I think cement production is helpful because you put CO2 away. It's not as big as you would like it to be because think about why steel slag and cement happily absorb CO2. They do because the material first got heated and gave off a CO2. And you started with limestone, calcium carbonate. You, in a cement kiln, converted it to calcium oxide. And you, by the way, put additional CO2 out to put the energy in. And now that you have done that, you have the option of putting the CO2 back on. In normal concrete, you instead put water on. So you hydrate it rather than carbonate it. And yes, you can carbonate it instead, but you cannot really take up much more CO2 than you started with. The exception is if you started with materials that had no CO2 to begin with, but they tend to be not very good at picking it up. But there are a few players in the game who try that, but it's very small. Most of it is taking materials which we have artificially removed the carbon from and putting it back on. So that is helpful in the balance because we would have taken it off anyhow, but it is not going to be more than a few percent on the total.
Great. Thank you. Thank you, Dave, for that question. And Jason, welcome to the stage.
Hi. Thank you for the discussion and thank you for the opportunity. I wanted to ask, let's say in 2040, 2050, we have hit the gigaton scale. We're doing 5, 10 gigatons of direct air capture. What do you see as having happened or what would need to happen in the next, let's say, 3 to 5 years to end up on that path, and which actors in society, be it national governments, corporations, investors, financial institutions, so forth, are the biggest kind of potential drivers to getting to that goal?
I think first and foremost, you need an economic driver. And to give you an example, if you take a look at a picture of New York in 1900, it's extremely rare that you see the car. If you look in 25, they're everywhere. So you can do things in a decade or two. The first jet plane got into commercial service in 51. By 65, the fleet was jet planes. If you look at how far cell phones came out of nowhere, smartphones came out of nowhere, how fast France could transition from an oil-based electricity system to a nuclear-based system, that was about 16 years. So if the drivers are there, you can do it quite fast. But in order for the drivers to come there, you need some regulatory framework which makes it happen. Now you have a few volunteers like Microsoft and Stripe who say we want to be carbon neutral and we volunteer to pay. But I think what it really takes is that carbon as a waste management problem needs to be attacked. And people say, well, it's just a waste and there's no money in it. But that's not true. Waste management, the company, picks up my garbage and I pay a good penny for that. In other words, they don't make goods out of my garbage, but they delivered a service for me, and I actually have no choice but to take it. I can't just bury the garbage in my yard or in front of my neighbor's house. And I certainly can't tell my neighbor, trust me, I'm mitigating, it's 10% less than last year, right? We need regulations which say you must not dump CO2 into the atmosphere. And based on that, you then will set the price of carbon. And by the way, the combination of air capture and sequestration will set the marginal cost. Because if you are costing more than that, it would be foolish not to use it. And if you cost less than that, it comes first. So this will be the price finding effort. The cheaper direct air capture and sequestration is, the easier this all will be and the faster it will grow. But to get from small boutique to ubiquitous, 10 to 20 years is enough.
Great. Well, thank you.
And once you are there, you can scale it up all the way. And I do think at some point you will need governments to say, we take our CO2 back.
Very good. Thank you. Eli, welcome to the stage.
Hi. So on your figures that you just mentioned, Klaus, about the area required for photosynthesis, what reference point we're using? We're using tropical forests, or we're using something else?
I was using something else. I was actually using intensive agriculture. Václav Smil many years ago wrote in Energy at the Crossroads, I believe. He wrote a very nice summary of that. Your standing forest is a tiny fraction of a percent because most of what the photosynthesis picks up, it lets go again. If you have intensive agriculture, you can get to about 1% or maybe a little more. Sugarcane can get to maybe 1.5. Some algae ponds can get even higher. But they are intense, and you are going to fertilize, you are going to water, you're doing all of these things. And at that point, you are intensive agriculture, and then you are a little more than 1%. So I can now turn around and say we are talking about 17, 18 terawatts of primary energy, which is the cost of like 40 gigatons. And how big an area of sunshine do I need at 1% conversion efficiency to have that much?
Okay.
So I've done the calculations actually for intensive cultivation of micro-algae, cyanobacteria, and the like, and to get to a scale where you're drawing biomass that affects the equivalent of over 100 gigatons of carbon dioxide per year. over 200 gigatons of carbon dioxide per year at a moderate rate of aerial bioproductivity of 50 grams per meter squared per day. That would require approximately 2.5% of the surface area of the ocean, for reference.
Any thoughts on that, Klaus?
Okay, if you, we are. I think we should sit down together and figure it out. 50 grams per day is an awful lot of biomass.
So,
well, that's in closed photobioreactors and involves nutrient recycling.
And how much light?
That's at one sun installation. That's average solar installation.
mm-hmm. Sounds like an interesting discussion to have, but not right here.
Yeah, I need to sit down and go through the numbers, but typically people talk kilograms per year per square meter. So if you do that 365 days a year, you are at very high efficiencies. And people have talked about 10% efficiency in sunlight conversion in algae. But when I looked at this, they always do that in the dark. If there is no photon there, the ability of the algae to digest that photon is incredibly good. Once the sunshine comes in, it gets harder and harder for reaching efficiencies like that. So I used 1% or so.
Right.
And then for perspective, I used to do it a long time ago. If you have a gigawatt power plant, that's 3 gigawatts of heat. That at 1%, that's about 30 by 30 kilometer of land.
Okay. Let's move on. Thank you, Eli. Karen, welcome to the stage. You have a question.
Hey, Klaus, you briefly mentioned mechanical trees. Can you go into that into a little bit more detail?
Well, one of the things we did, apart from the moisture swing, is we said, which actually motivated me. I started out with the observation, can you possibly do this? And I said, well, look at a cubic kilometer of air, and I can convince myself that a big windmill actually sees this in an afternoon. And I can ask, if I value kinetic energy at 5 cents a kilowatt hour and it moves around at 6 meters a second, I can calculate the energy content of that cubic kilometer, and it comes out at $300. And apparently it pays to put a windmill up to harness that $300 worth of kinetic energy, and you get a fraction of it. If you are willing to pay a tipping fee of $30 a ton for the CO2, that same cubic kilometer contains $21,000 worth of CO2. So rather than trying to figure out how to get air through the gills of my system, I think of it like a windmill. It stands in the wind, and that makes it like a tree, right? The air blows over the leaves of the tree, and the trees take the CO2 they want and add the water they don't, or they can't help giving up. And so in that sense, these are mechanical trees. They are surfaces. And Carbon Collect, the company ASU is working with, has designed a tree which you can think of as a vertical column of 150 leaves, which are discs in the diameter of the column. So if you're old enough and have seen these polyvinyl record players which had a whole stack which fall down one at a time, we have a column of those discs, 1.5 meters, 5 feet in diameter, about 2 inches apart, 150 of them hanging in a column. And every 30 minutes to an hour, they've let down into a drum at the bottom in order to regenerate, and then they come back out, and the process repeats itself.
Yeah, it's a very cool design, by the way. I saw it in Klaus's office. It's a really, really clever way to do it.
And because it's round, it doesn't care which way the wind blows.
Exactly. It's very cool. And by the way, just for people to understand it, the way I describe your system is those discs are made of a material that holds on to CO2 when it's dry and releases it when it's wet. So basically, you put it up in the air, and the dry air, the air itself dries it out. And then once it's dry, it starts collecting CO2. And when it gets saturated with CO2, you collapse it into the drum, which is puts water or moist air, and then the CO2 comes off the discs. You collect that, and then you stick it back up in the air to dry out, and repeat the cycle. Did I get that about right?
Yes, except because now we also want to work in a wet climate, we can feed into the discs various materials.
Okay. All right. Good.
So we are not limited to moisture swing, but we certainly can do that.
Yeah, and then there's also thermal swing, which is the way Svante and Climeworks do it. And that's a material that holds on to CO2 when it's cool and releases it when it's warm. And so basically you cool it off the material with air, you put it out, you flow air through it, and then that absorbs CO2. And then when it's saturated, you inject some steam, and that knocks the CO2 out of it. And you collect that, and then you repeat the cycle by cooling it with air again. So that's what a temperature swing. There's also electrical swing being worked on. There's already pressure swing, but I don't think pressure swing is going to make it in terms of the efficiency compared to other things. And there's different swings where basically capturing and releasing CO2, and that's what we're talking about here. Thank you, Karin and Nisha. Welcome to the stage.
Thank you, Dan. And my question is related to the in-between. So I was very gung-ho on solutions, and then it hit me with the heat dome and the fires that we need to do something in the interim. So I would love to know what solutions you feel would get us to scale till we're ready to scale DAC. And then my second part of the question is about your work and how we can potentially help you scale that as well.
Well, it's an interesting set of questions. The scaling on our work, I have taken the attitude, and I worked with one of my students wrote a PhD thesis on this, is that economies of scale work. Economies of scaling up in the past required that unit sizes got larger and larger. We argued in that paper from 2013 that the economies of mass production are even better, and witness the fact that you can think of a car engine as a power plant of sorts, and the internal combustion engine is about 100 times cheaper than a power plant per kilowatt. And it always struck me as interesting, why is this? And I think the way to scale up is to figure out how to do things small and stay small and number up rather than scale up. That, by the way, requires a lot of automation. We made the argument in that paper back then that the real reason scaling up in unit size was to simplify control problems and not have 10,000 operators in a gigawatt power plant, each operating a single 100 kilowatt machine, which is the size of a car engine. But if you can automate and you can have a computer take care of that, then you don't need 10,000 operators, and you may still have the 30 operators who would be running around in that power plant anyhow to run the automated version. And so I believe that this is the way things will get there. But I do think integrating on the larger scale with renewable energy is probably a very, very powerful thing to do. So I would like to say that we open the door for photovoltaics to run all the time. If you want to store electricity for hours, the battery is what you want. If you need to store electricity to deal with mismatches between summer and winter, you need a chemical storage. And so what we can offer renewable energy is 100% penetration, because what it takes is cheap electrolyzers, and which can afford to sit idle most of the time, and electricity, which raw electricity from a photovoltaic panel is coming down to a penny a kilowatt hour before it enters the grid. I took the inverters away from you. And that electricity could be used to make hydrogen, and then we can make fuel. And if you do that, you actually create an environment in which we can pull the CO2 back. And if you now have a regulatory framework which says you're not allowed to dump CO2, it actually can come together. I'm working with the student who was the PhD candidate who wrote most of that paper, Eric Dahlgren, and he recently formed a company to make fuel. He called it Aircella. Aircella.com is a company whose goal is to make fuel from air capture at the retail level, at the household level. So you have a device which can provide the amount of fuel you would need on a daily basis. And that could be a hybrid, or it could be a second car for long distances. And all of that can be done nowadays. And he is trying to get this economic in the next few years.
So, but any suggestions on how people can support your work? Like directly support or indirectly, or do you need any?
Well, we are working at ASU, and as any other university, we need help and support. We need people. We need to be able to pay people.
Is there a website? Do they go to your ASU website, and then so they can actually support your program within the university if they wanted to? If there were,
you can do that, yes. And we have had that on not whoppingly large scales, but we had it. People came and said, we want to support this work. And we can use that.
Okay. Very good.
And the university has people to make sure this is done in an official and proper way. You can't give it to me and I'll stick it in my pocket.
Right. Very good. Hey, I want to welcome Glenn to the stage. Glenn, welcome.
Hi, thanks very much. Another great conversation. And before I start, I think we need all technologies and biologies, any mechanisms possible to get as much carbon out of the atmosphere and back into the place where it's needed, which is part of my discussion. So my question is by sucking CO2 out of the atmosphere via DAC, direct air capture, what is replacing the oxygen? And the second bit of the question is, by bypassing plants to sequester the CO2e into the soil carbon, what carbon energy in the form of soil organic carbon, what humans and other life forms are made of, what's going to be there to support life going forward? Thank you.
Well, right. The first observation is, as long as we burn fossil carbon, we are removing oxygen from the air. And that has actually been demonstrated. On the other hand, we are in a somewhat lucky position that with the CO2, we worry about 100 parts per million. The oxygen in the air is 200,000 parts per million. So if you change that by a couple hundred parts per million, you haven't changed everything yet. But it's another good reason why eventually you have to stop. Right? But if you burn fossil carbon, that problem doesn't go away. If you burn synthetic fuels, you do at the end of the day get your oxygen back, right? Because if you convert CO2 and water into hydrocarbons, the byproduct of that is the oxygen, which was used when you burned it in the first place. So you literally unburn it so the oxygen comes back out. So a world which recirculates liquid hydrocarbon fuels for those applications who need it is actually not affecting the carbon balance in the system, nor is it affecting the oxygen balance in the system, because both cycles are kept stably. Lastly, if we keep CO2 at a level as high as it was naturally, we are not stealing from the biosphere. We are, as a matter of fact, you may have complicated impacts on this if you grow forests at a very large scale. But you are at the end not all that. You are not if you do it with air capture, you are not affecting this balance at all, because you're not pulling it out. Now, if you were to drive the CO2 down to 30 parts per million, then of course you would. But the idea is we keep it at a level that is acceptable and tolerable, and presumably a little higher than it was in 1800.
Great.
I don't think you get people to agree to keep pulling until we are below 280.
Right.
But 350 we might get to.
Okay. Well, thank you. Chanakya, welcome to the stage.
Thank you, Dan, for having me, and thank you, Klaus, for answering our questions. I have a quick question that was related to what Eli was mentioning. I read somewhere that our oceans absorb more carbon dioxide than all the plants and trees combined. One, is that true? And just curious, are there any ways to make that even more? Thank you so much.
Yes, the answers are yes and no. The uptake of CO2 by the oceans is very large. And the reason is very simple. The ocean is slightly alkaline. And if you put CO2, which is an acid in the atmosphere, it will dissolve into the ocean. And so the ocean takes its part. And that's a large part of the total. You can see that it does that. The top 100 meters of the ocean are effectively in equilibrium with the air. And it then gradually works its way deeper and deeper. But the bottom of the ocean hasn't seen anything yet, because it takes about 1,000 years to get there. By the way, that's too short to say it's permanently put away. But the oceans have a capacity to hold CO2. And by the way, if you pull back, it comes back out. You don't really want that to happen, because what you are doing in doing so, you're acidifying the ocean. And if the pH of the ocean drops, you ultimately dissolve coral reefs. At about 1200 ppm, coral reefs on the surface would simply dissolve. As you get higher in the CO2 concentration in the air, and therefore the pH of the ocean drops, it has been measured at Biosphere in Tucson 20 years ago, that the result of that is that the ability of the coral reefs to grow is rapidly deteriorating. And the reason behind that is the ocean is actually supersaturated in calcium carbonate, and if you lower that supersaturation, it becomes harder and harder for the corals and mussels and other calcium carbonate formers to actually do their job. And you can actually tell that they have a harder and harder time. In the biosphere context, they had an artificial ocean. They could show that the uptake rate was linearly related to the oversaturation. And when we started this game, we were 5 times oversaturated. Now we are about 3.5 or so, or 4 times oversaturated, and so it gets worse. And so the good news of air capture, and people sometimes make there's a criticism. They say, well, if you have to do air capture, you actually have to pull 2 tons out, because the ocean will give back its ton. I actually think this is good news, because when you emitted a ton, you could have stopped it right there. But now half of that ton is in the air and the other half is in the ocean. And the nice feature of air capture is that it actually gets both halves back.
Mm-hmm. Very good. Well, thank you. And Joshua, welcome to the stage.
Thank you. Thanks, Klaus, for dedicating yourself to this important intention. 2 questions. What is the embodied energy of making one of the mechanical trees, including extraction of materials, transport, assembly, maintenance over the lifespan, etc.? And the second question is, have you fake news proofed your plan of attack here, or made it human nature proof? Thanks.
Can you repeat that last part? Has what made?
Have you made your strategy immune to fake news? In other words, if you come up with a vaccine that can help people,
If you know how to make things immune to fake news, let me know, because I don't know how to do that. But
I
we are
don't think I do.
trying. But
I hope you do.
But I give you a simple way of looking at it. We have embodied materials in our system. If we wanted to build the system strictly with the CO2 we collect, right? Because if I can make fuel, I can clearly make plastics. And so if I just wanted to do this, I did an estimate because we don't want to use steel if we can help it. So think of this whole thing built more or less out of plastic parts, and the sorbents are hydrocarbon-based resins. So we can do that. I estimated rather liberally that for every ton we collect, we need to set 20 kilograms aside. And then we have enough stuff to make it work. I got into life cycle analyses when I was at Columbia, and one of the things I learned for most things, and so I can now do it for air capture in general, a kilogram of material is responsible for a few kilograms of CO2. There are exceptions to that, but think hydrocarbons, well, yeah, if you burn them, they triple their weight. If you look at steel making, there are a few tons of CO2 attached to a ton of steel. If you look at it from that perspective, a car engine produces far more CO2 than went into making it. And we are the reverse of this. We are collecting our own weight in CO2 in weeks. So as a consequence, the amount of embedded carbon in making the system is small compared to the lifetime uptake, and that's reflected in that 20 kilogram where I said, well, let's just turn it around and make the thing from itself. So the amount of carbon we need is very small compared to the amount of carbon we capture.
And Klaus, I remember you telling me, I think 10 years ago, and this really struck me when you said it, you said if we run the carbon capture, your particular carbon capture system on coal power, it would only reduce its efficiency a little bit. Do you still have those numbers in your head?
Well, I for that particular device we were looking at back then, and we are still at about that level. If you were foolish enough to acquire your power by buying it from a coal plant, you lost 30%. Mm-hmm. In other words, but we are working hard right now on running on intermittent power. And the advantage of intermittent power is that I can go into very cheap renewable energy when nobody wants it. And I still think it is a good figure of merit that your energy consumption is much less than the energy associated with making that much CO2. But it is not critical now, because I give you another example. People tend to tell you, but you make less energy than you put in, right? Think of a power plant, right? A power plant has a 30-40% efficiency, which means that the energy in was 2.5 times the electricity out. Nobody complains about it. In some way, it's a rhetorical tool. Now, if you are trying to fix fossil energy by picking up the CO2, then indeed you cannot go past get past that hurdle. But if you say my liquid fuels are limited to high value applications, does it really matter that the embedded energy in the jet fuel was more? Now, of course, less energy is cheaper, right? So, and I think it's fair to say that the energy used to make that synthetic fuel is more than the energy you put in, but the contribution from the air capture technology is a small fraction of the energy embedded in
You're right,
that fuel.
and people don't realize it, but only 1% of the energy in a gallon of gasoline goes to moving you, and 10% goes to moving the car. So, and everyone's happy with that. They don't mind wasting vast amounts of energy to get something done. So, I agree with you on that. It's a good point.
But my point really is we aim to make quality energy and balance the carbon budget, right? And as a consequence, we don't have to exactly get that balance right. But of course, the lower we are, the better off we are. And I think most technologies, with the exception of calcining limestone, are by now well below the energy which was available in the CO2. And thermodynamically, you can get a lot better, because if you look at it, if you burn a gallon of gasoline, you get 700 kilojoules out. Thermodynamically, it takes you 22 kilojoules to get that CO2 back. Now, today, we are nowhere close to the thermodynamic limit, but we can work on that. Right? Our process with the moisture swing was 50, but we are cheating because we got half of the energy by using water, and we didn't count that. Right? That wasn't energy, that was water. Right? So effectively, and if you use a thermal process, you're probably closer to 100. But you got 700 out when you burned it.
By the way, speaking of excess energy, are you aware of the work of Tony Seba and the Rethink X group, which says if you overbuild solar and wind by 400% in order to reduce the amount of storage needed, so that even on a cloudy day you have 100% of the energy you need, that provides excess energy about 80% of the time, which could be used for carbon capture and desalinization and things like that. So that would be a very inexpensive way for doing it.
And in a funny way, you need this anyhow. When I was at Columbia, I taught a class on alternative energy, and I wanted to break people's thinking about how energy has to be electricity. And I said, in order to make this happen, think of a hypothetical energy source, which is, of course, fake. Somewhere in the Southern Ocean is an island which has a voltage between its two ends, and you can draw any current you like. But unfortunately, this thing turns on and off in an unpredictable fashion, but half of the time it's there, or a third of the time it's there. So now what are you going to do? Are you going to run a power line, an orange cable all the way back to New York, or do you find a smarter way of taking this energy, which is essentially free? And all the students agreed we make chemicals out of it. We make hydrogen, and then in order to ship it more easily, we convert it to methanol, right? Which with air capture you can easily do. And I said, the reason you thought this way is because the energy was free. Right? If you started with a solar panel which made 20, 30 cents a kilowatt hour electricity, the only place you could put it was on the grid. But if you have a solar panel which makes excess power at 1 cent a kilowatt hour before it goes into the inverters, you are now having a primary energy source of about the same cost as natural gas is today. And it's already electricity. So it's cleaner. And I suspect we figure out how to harness that. But if we convert that into liquid fuels and we run 2/3 of the day on that energy without sunshine, well, then don't be surprised that the amount of photovoltaic which feeds those systems is more than what goes directly into the grid. We haven't quite yet figured out that there is a revolution happening in the photovoltaic side, that this stuff is now so cheap that it can do that. And we have to get all the other bits and pieces of the story lined up with us, and we haven't done that yet. We haven't figured out how to deal with electrolysis cheap.
Yep. But we're working on that, though. So
Because
I
an
mentioned that
electrolyzer,
earlier. Yeah.
yes, we are working on it too. If your electrolyzer costs $500 a kilowatt, it must run day and night.
Mm-hmm.
So you have to get it to $50 a kilowatt, and now you can afford sitting idle most
Yep.
of the time.
I think that's going to happen later this decade. I think we're on a path for that.
And I think it will happen. And with that, you suddenly have 1 penny input and 30% efficiency. So the electricity coming out is 3 times more expensive than the electricity came in, plus all the costs you accumulated on the way. And if your electrolyzer was cheap, that's not very much.
Very good. That's great. Let's move on to Joseph. Joseph, welcome to the stage.
Well, thank you, Dan and Klaus, for this interesting and wonderful session. You spoke about CO2 in the ocean, and I have like 2 questions to ask. We agree that the technologies to capture CO2 back in 2 decades were just in the theoretical way, but now we are glad that they're happening. One of them is the CO2 capturing from the ocean, which is yet to be deployed. One of the challenges being the price, especially due to energy demand. What do you think? Should we put more emphasis in CO2 capturing from air, or should we apply both of them, CO2 capturing from the ocean and from air, working simultaneously to have a significant impact in reducing the amount of CO2 in the atmosphere? Another question is, what's your take? Where do you see the indirect air capture in the next 5 or 10 years? Thank you.
I nearly consider capturing from the surface ocean as equivalent as capturing from the air. The reason I chose air, and Matthew Eisenman and I have slightly different outlook on that. The reason I chose the air is that 1 in 2,500 molecules in the air is a CO2. If you look at the ocean, the carbonates and bicarbonates, rather than the CO2, the direct inorganic, the dissolved inorganic carbon, in other words, is 1 in 25,000 molecules. So while it's denser in the ocean, which is what Matthew points out, it is more dilute because there are more water molecules relative to the carbon molecules in the ocean than air molecules versus CO2 molecules. Furthermore, the air mixes really well, whereas the ocean is not quite as good as that. It follows a streamline which mixes well, but the ocean as a whole doesn't know that about it all that much. So I think at some level it's easier to collect from the air. On the other hand, if you have a good idea how to do it from the ocean, I would treat it as absolutely equivalent. And keep in mind, if you remove it from the surface ocean, the air will give it to you. And if you take it from the air, the ocean will give it to you. So the two are utterly equivalent. And thermodynamically, by the way, they are perfectly equivalent because the two systems are in equilibrium.
That's great. Anything else there? Or was there a second part of the question?
Yeah, there was a second part.
Joseph, what was your second question?
The second question was, what is your thought? Where do you see CO2 capturing from the ocean in the next 5 or 10 years?
In the
CO2
next
from
5
the
to 10
ocean?
years, where do you see that going?
I don't know. And the reason is that so far the technologies which have been demonstrated are not easier than those from the air. And I think this is a field which needs a brand new idea. If you have it, it can be a game changer. If it's not there, I think the ocean is not playing.
Do you think we'll see some from the Elon Musk X Prize carbon removal challenge? And are you working on that at all? Part of it?
No, because we're working with a company, and I feel it can turn into a distraction.
Okay. A lot of people on Clubhouse working on
we
that
have a
on that challenge.
yeah. I'm just afraid you jump through a whole bunch of hoops meanwhile. And yes, but by the time you win the prize, you don't really need
Right,
it.
if you already have the solution, yeah.
And in a funny way, I was also burned by a previous prize, right?
There wasn't. That's true. There was the Richard Branson prize that a lot of people worked on, and I don't even know exactly whatever happened with that. I never really followed up, but obviously it didn't work out.
It became a debating club, and it wasted everyone's time. So I think we are better off to buckle down and do things.
Let's see. Landon, welcome to the stage.
Hey, hello. So I think actually Joshua sort of asked a large part of my question, which was sort of the embodied energy and the in the supply chain and extraction to produce these. And I'm also wondering, Klaus. So I just keep up with this stuff sort of out of the periphery. I know that other people like David Keith have been working on direct carbon capture and storage in various subterranean manners. I think they tried it in Australia, invested quite a bit of money, and did not get a lot of return. So I'm sort of wondering where we're at with actual demonstratable carbon capture, and also why. I guess not why, but the stats that you cited for carbon capture and storage in land based on forests are probably correct. But I'm wondering with the intensive agricultural thing, where you're at on that, because through understanding like the role of fungi in carbon mobility and carbon pathways, soil carbon pathways, and also implementing things like pyrolysis of crop waste, right? Like this carbon that we're already cycling, and trying to arrest that and capture the energy off of it in a way that's sort of scalable locally and regionally. I think the potential there is somewhat high. So I just wanted to push back on that. Sorry, those are two totally separate things.
Well, I'm not telling you that the biomass approaches are not useful. I'm pushing back on the opposite story, that it's plenty and it's all we need. Right? And we need biomass approaches right now because they are available. On the other hand, you have to be careful how far you push them. Again, going back to an old lecture when oil was more than $100 a barrel, my students got all excited about biofuels. And my response was, yes, and it works, and it's even economic at this oil price. And therefore it will happen. But my concern is that an SUV is far hungrier than a person. And unfortunately, for some parts of the world, the SUV has a wallet which is much thicker than that of most people in the world. And we are committing 40% of our corn crop to making fuel. And that corn is not available for people who are hungry because they can't afford it. So biomass works up to a point, and I think the first gigatons per year, you can get that way. But if you're really talking 40 gigatons, you are really, really big. And yes, 50 grams per day is a large number for biomass collection. I'll come back to Eli's point. It's not utterly impossible, but 2.5% of the ocean is a very large amount of land. That's 7.5% of the land area on the planet. And it is, and I think agriculture is about 10%.
And the United States is less than 2%, by the way. Just a little framing. The United States is less than 2% the area of the globe.
Yes. So my point is, your footprint is still very, very large, and I think we have to find a way of accommodating across this board. I'm actually very supportive of reforestation because I think it's a good thing. I'm even supportive up to a point of afforestation as long as we keep in mind that there are limits to it. And the palm oil plantation scale with the Europeans after Kyoto was real. And the amounts of carbon we are talking about in all of these discussions is minuscule compared to what we need. But it had some real environmental impacts. So we have to figure out how to draw a balance in all of that. And I do think that, yes, you can put quite a bit of carbon into the soil. And we should. We certainly should put the soil carbon back we lost. But that cannot take care of the CO2 we have put out because it wasn't responsible. The ones we lost weren't responsible for the bulk of the increase. There's no expectation that taking it back will fix the problem. It will contribute to fixing the problem. And therefore, I think it's actually very important that we come up with broadly available ways of certifying carbon capture and disposal and storage. And that has to account for permanence, and that has to account for who is responsible, and it has to get past the offsets we have right now. Even with all the effort we have right now, one of my postdocs has pointed out that in 60 years from now, 50% of all the carbon sequestration people buy right now voluntarily is not assured anymore because there were no guarantees past that point. And that just pushes the problem from us to our kids or grandkids.
Right. Okay, thank you. Mega, welcome to the stage.
Hi. My question was, I think you mentioned just the need for governments and entities to promote policies that actually support carbon capture for it to get to the scale it needs to get to, which makes a lot of sense. So my question, I guess, is I think about some of the groups that oppose these types of solutions, and it feels like a lot of the opposition, it'll be framed in terms of questioning the economics or the technological feasibility or things, but I feel like it fundamentally comes from distrusting technological solutions to these types of problems or from distrusting anything that the oil and gas industry has touched, thinking about EOR and things like that. How do you think about convincing people who oppose this and getting us to a place where those kinds of policies can actually be implemented?
It's a very hard question. We currently have a technological solution for COVID vaccination, right? And we're not doing all that well with it. So I think it's a challenge. I think I've often asked, what's the role of the oil companies? My answer is consistently, they are in a good position to help, but they are also not likely to help because culturally this is very hard on them. And I think they end up like IBM and the PC. They have every chance to be in the lead and they aren't. And in a funny way, that may help with solving the problem. Carbfix is a good example. That doesn't involve oil. And maybe if it becomes a new sector in its own right and is tied to renewable energy, it all gets a little easier. But the politics of this is very messy, and I think the last thing you want to end up is being caught in that polarization.
Yeah, I also think as we see more and more climate impacts getting worse and worse and worse, people are going to start asking for more solutions and be willing to maybe pay for them. Again, in my point of view, we just need the incentives put in place, and there seems to be some bipartisan support for at least doing the R&D and providing incentives. The 45Q that Klaus mentioned earlier as a tax incentive was signed by President Trump, so which is not a climate friendly person. So I think there's some opportunity to at least demonstrate that this is all real and can work. And then once people understand that, then perhaps there will be a more public support for it. Right now, people are still saying it's a fantasy, it doesn't work, it can't scale, it's too expensive. I think Klaus did a good job today explaining to us how all those things aren't really true, even though he said there's certainly risk in further development. So I think that's everyone who asked questions. If there's anyone on stage who didn't, I think everyone did. You can unmute right now, but I think we covered that. So with that, I want to just leave it to Klaus to maybe sum up his thoughts on this, or is there anything else you're working on that you want to tell us about that you're excited about?
Well, we are trying to reframe this as a waste management problem, and that I think is important. But I would also say we need to figure out how to build bridges. And I know today I came across as pushing back at biomass approaches because I think inherently they have limits in scale. On the other hand, I think we are better off teaming up. And I would point out that in the next 5 to 10 years, I think you will see far more carbon being taken care of by biomass than by air capture. And that's a good thing because, think again, we live in an overshoot world. The problem is not anymore, how do I put the brakes on and come to a stop? But how do I turn around and get back to where I was before? And if we can avoid an emission, or if we can mop up an emission today with means which are ready to go, by all means we should do that. So I think we should figure out how to be allies and teammates rather than think of this as a zero-sum game. As a matter of fact, this pie is so large that there's plenty for everybody.
Yeah, I think that's great. The great way to finish up. So, Klaus, I want to thank you so much for your time today. As always, I always learn so much from listening to you. I love the way that you think about these problems from first principles points of view, and that's really helpful. And I think you've helped the audience to understand about the challenges and opportunities of carbon capture. And thank you so much. And again, thank you to everyone on stage and everyone in the audience for coming today.
Okay, thanks so much. And unfortunately, I have to leave. I'm already in my next appointment.
Bye-bye.
Take care. Bye-bye.
That concludes our interview with Klaus Lackner. If you'd like to listen to our other interviews, please search for Climate Chat Club on YouTube. Thank you for listening.